All right, happy Friday, everyone. We're going to pick right back up where we left off on Wednesday with sorts. We were just sort of discussing heap sort as we broke for class on Wednesdays. So take a minute or two, turn to the people around you, and try and remember what's selection sort, what's insertion sort, and what's heap sort, and then see if you can remember the answers to these questions about the sorts. So see if you can describe the algorithm to one another. Go ahead, take 90 seconds. All right, let's start with selection sort. Does anybody want to remind us what the algorithm for selection sort is like? Can anybody describe that algorithm for us? Or even a part of it, frankly. We can build it up together. Okay, maybe we'll start with some of the questions. Okay, is selection sort an in-place sort? Can anyone remind me what an in-place sort is? What does that mean? Beautiful. Yes, yes, yes. It doesn't take any extra space. We're just sorting within the original array that we were given. What about stability? Is selection sort a stable sort? Yes, I agree with y'all. It is not a stable sort. Can somebody remind us what stability is? Two items that are initially equal, so in some aspect that you're initially sorting on are equal, that after everything is sorted, they remain in the same original relative order. If you remember, my example was like, what if you had like a 5A and a 5B, and originally 5A was earlier in your collection than your 5B. A stable sort would ensure that they remain in that relative order, but eventually when they're sorted, they'll be next door neighbors, right? Because they're right next to each other. And you might be like, what the heck is a 5A, Casey? That doesn't make any sense. And remember, stability really only matters when what we are sorting is a complex object that can be sorted on more than one dimension. So my example is maybe we sort first by last name, then we sort second by first name. A stable sort would ensure that whatever order that initially is in last name, you would remain in the same original order. Okay, what about the runtime of selection sort? What's the worst case runtime of selection sort? N squared, yes. We've got those nested for loops. What about best case scenario? Also n squared. So that means our in practice runtime, n squared. So to remind y'all how the algorithm works, we have two sort of subdivisions of the original array. Originally, everything is unsorted and nothing is sorted. And then we look at index 0. And what we're going to do is we're going to scan over the unsorted portion of the array, looking for the smallest value. When we find what the smallest value is, and that does mean we have to get all the way through to be sure, like this is the smallest, then we select that item and we swap it with what is currently at the place we know that thing belongs. And then we now have one item in our sorted list and then one fewer item in our unsorted list. And then we just sort of grow the sorted list to the right and the unsorted list shrinks. So selection sort, the way I remember it is you're scanning through the list and you're going to select what belongs at this place. And then you swap. Questions on selection sort? Cool. Okay, what about insertion sort? Does anybody want to remind us how that algorithm works? Anyone remember that one off the top of their head? Thinking about it? Okay, maybe I'll start with the easier questions then. Is insertion sort an in-place sort? Yes, we're sorting within the original structure. We don't need any extra space. I'm holding all of my exam papers in my hands and I'm just like swapping them around here. I don't have to lay anything out on the ground. Is insertion sort a stable sort?
No. I don't think so.
It's so tricky. It's so tricky. And I guarantee you there are definitely implementations of insertion sort that can muck this up. But insertion sort, by our functional implementation, is a stable sort. And the reason that insertion sort is stable, whereas selection sort is not, is insertion sort has the same idea, right, where you have like an unsorted portion of the list that grows or a sorted portion of the list that grows and an unsorted portion of the list that shrinks. But in selection sort, you're looking through the unsorted portion, finding something, and then doing the swap. And because of the swap, we're not paying attention to what was in the space we're trying to free up. So we could just be like sending that thing off to the back of the list. We're not really paying attention. So we're sort of destroying that original order. Insertion sort, instead, we start and we look at the very first item in the list and we ask that item, are you smaller than the item to your left? And since there's nothing to its left, the answer is no. And so automatically the first item will always stay in the first index of insertion sort. And then we look at the second item over and we ask, are you smaller than your leftmost neighbor? If you remember our delightful Hungarian folk dance, that's when they would come out and they would do their little partner swaps. Because what insertion sort's going to do is it's going to, at that sort of like threshold between the sorted portion and the unsorted portion, it's going to do little swaps down the line until it sort of like sort of floats and finds its place where it ultimately belongs in the relative order of the sorted set of items. It is technically operated by those swaps, but if it helps in your brain, the way that you can kind of think of it is that when you come to the next thing that is at like the leftmost of the unsorted list, you're going to scan through the sorted list and then insert it where it belongs, thus shifting everything to the right. So that's where the word insertion comes from, because we're picking something up and we're putting it where it belongs and we're inserting it and scooting everything over. Selection sort doesn't do any scooting. It goes and it finds exactly what belongs in that place, and then once it's placed something there, that's its like forever home. So one distinction between selection sort and insertion sort is that in insertion sort, we don't have a correct sorted order guaranteed until we finish the entire algorithm, right? Because we don't know what we're going to sort of encounter in that unsorted portion. Selection sort, though it has sort of like the least optimal, best case and worst case and all that stuff, it does give you this opportunity. If you only care about sorting the, first 5 items or something, you can quit selection sort after 5 items and it would give you the smallest 5 items. Insertion sort doesn't do that. You got to finish, all the way through to get your goodness. But what is the worst case runtime of insertion sort? N squared. Yes, it's still got, remember, it's like, because it's got those sorted lists and unsorted lists, and it's like looping over both of them and doing the swapping. It's got nested loops. Its worst case scenario is N squared. But because at each moment we're looking at the next thing in the unsorted set, and then we're asking it, how far do you need to move to find your like ultimate resting place? If the thing is already where it belongs, then I don't even need to do any work. So what is the best case runtime of insertion sort? N. Exactly. So again, eventually, I feel like I do this every single quarter as I go on the internet and I like Google each of the sorts again, and like the biggest Googled question is like, what is the best sort? As if there is like one to rule them all or something like that. And there's certainly ones that we think of as fast. There's certainly ones that we think of as memory efficient, but you can see how each sort has a slight different nuance to it. And you want to make sure that you're picking the sorting algorithm that fits your scenario best. I'm saying this because today exercise 6 comes out, and that's exactly what you're going to be doing on exercise 6 is we've got a bunch of different scenarios for you. You're going to pick which sorting algorithm fits best. And then we sort of left off with heap sort. So heap sort is that so very complicated sorting algorithm that's just like, hey, we've got this data structure. It already does some really useful stuff for us. Just like dump everything in the data structure and call remove min, you know, n times, and you got a sorted thing. So I don't think we've actually gotten a chance yet to talk about the stability or the in-place running of heap sort, or even the runtimes. Does anybody want to take a guess, maybe? Since I don't think we've discussed it as a group, what do we think the worst case runtime of heap sort would be? We're gonna guess. N squared's a good guess, right? So far they're all n squared, and like chances are it's gonna be an upper bound of some kind, right? Yeah. N log n, another really good guess, because we know we've got that heap in there, and heaps have that sort of like n, or that log n runtime, right? Log n to add, log n to remove. But then we also have that miracle that is Floyd's build heap that lets you build a heap in linear time because of a bunch of fancy math that Casey put on a slide and then didn't subject y'all to actually going through. But Floyd's build heap runs in n time, so we can build up the heap in n time, and then remove min, that is a log n runtime, so then maybe we end up with like n log n sort of runtime. Oh, wow, I didn't think I even had differentiation. There we go. So let's sort of like finish up our conversation about heap sort. I think we watched the video about it, but okay. Wait, didn't I? Okay, I thought I changed this slide. I'm just going to refresh these right now. Is there another slide down here? Oh, no, it's just I have duplicate slides. That's what it is. Okay, so with heap sort, remember, whenever we call remove min, we're going to take the thing that's at the very bottom of the heap, and we're going to swap it up to the top and then let it percolate down. That swap there is what's going to destroy our stability. So heap sort is not a stable sort. And if it helps, pretty much anytime you're sort of like swapping items like that and you're not sort of just like iterating through based on their original order, you're going to destroy stability. So heap sort is not a stable sort. Now, with heaps, we know that theoretically they look like a tree, right? But I subjected all of you to implementing them with an array. So, can we make this sorting algorithm an in-place sorting algorithm? And the answer is yes, if we get really clever. So, here is an array that represents a heap. And remember, when you're sort of doing that array representation of heaps, you kind of just like fill them from left to right, from the overall root down, going left and right. So this is a valid heap, I promise you. And what we're going to do is, you can see again with my little items here, we are going to have this sort of idea of like dividing within this array between what we've processed and what we haven't processed yet. And so right now, we're going to consider everything to be in the heap, and this little like sad fork over here is the sorted items because nothing's sorted. So what we're going to do is, we're going to call remove min. And we know that when we call remove min, what we need to do is we sort of like return that item, and then we swap in the thing that's at the very bottom of the heap, right? Well, if you remember from the implementation, that item exists at size index. right? Or size minus 1, technically. Like this 22 hanging out over here, that is the bottom rightmost element in the heap. And I know that it needs to swap in and take 1's place. And because we've removed min, then what we've done is we've reduced the size of the heap by 1, which is very convenient because now we have exactly 1 extra space left over in this array. Let's just like keep the 1 over there. So now we've called remove min, we've swapped in 22, and we've put the 1 over to the most extreme right where that 22 used to be, because now I don't need that spot for my heap anymore, right? Like I've reduced the number of items that are stored in the heap by 1. I swapped that item over in, and now I'm going to have to do my percolate downs until 22 ends up where it belongs, and then, you know, the 2 kind of percolates up. And then I'm going to do the exact same thing where I am going to remove min on 2, which means I'm going to take this 20 and swap it into the 0th index, which frees up the 8th index, and I'm going to put the 2 over there. And then I'm going to reduce the heap size by 1 and increase the sorted items by 2, so that as we continue to iterate, eventually what we will have is a shrinking heap and a growing set of sorted items. However, the growing set of sorted items, as you can see, they end up in kind of reverse sorted order. But I'm willing to live with the reverse sorted order because I'm getting clever about just repurposing the parts of the array that the heap doesn't need to use anymore. So by doing this sort of clever, like, store it at the end of the array that we don't need anymore sort of move, we can create an in-place sort with heap. Questions on how that algorithm works there? Yeah, we swap. Cool. So here you can kind of see how it's, you know, like a few more iterations shaken out. So we've got our sort of reverse sorted order here, 1, 2, 4, 14. 15 is now currently the minimum value sitting at the overall root top of the heap. If I was going to call remove min again, then what I would do is I would swap in the 22, I'd move the 15 over there, and then I would reduce the size of the heap, and so on and so forth. So we kind of talked about it briefly, but now that we've talked through the algorithm a little bit better, what do we think is the worst case runtime of heap sort? I heard somebody say it. Yeah. And if it helps, we can break it apart, right? So first we need to consider the runtime to just actually get everything into the heap. And we're going to use Floyd's build heap for that, so we're going to consider that n runtime. So we always have to incur n runtime just to get everything into the heap. After I've done that, I need to call remove min n times. What is the runtime of calling remove min on a heap? Log n. Yes, exactly. Because we got to do the percolate, and the percolate travels the height of the tree. So anytime we travel the height of a tree, that's a log n runtime. So that's where we get our n log n runtime, because we need to call remove min n times, and each remove min call incurs a log n sort of expenditure. Does this runtime change in a different case? Is there a difference between the best case and the worst case scenario for the runtime of this heap? I agree. No, there's no difference here. Either way, we're going to have to do these things where we sort of like swap in the thing from the bottom of the heap. And since we're actively pulling in the thing from the bottom of the heap, we know it's likely going to have to travel the entire height of the tree, probably back down. So each of these like percolate downs that get triggered after these remove mins is probably having like a big item that got put at the top that now has to sort of travel all the way back down. So we end up with an n log n, best case, worst case, and also in practice runtime. Is it stable? No, good, I said that. Is it in place? Yes, huzzah, okay. And as of right now, I will say heap, I know I mentioned it before, but don't sleep on heaps, y'all. Heaps are so useful, and heap sort, I don't know why heap sort isn't more popular, isn't more famous, It's doing the most. It's doing a good job. It's in place. It's got that n log n guarantee. Real nice. Okay? I would argue that heap sort may be the best sort. I know. If somebody out here knows about QuickSort, you'll say blasphemy, but I will fight for heap sort. Okay, so that's sort of the end of these three. We're going to pick up 2 more algorithms by the end of lecture. But does anybody have any questions about these ones? Yeah.
Why is it not stable?
So it's not stable because when we do that swap in from that item at the bottom of the heap, that's disrupting its original order kind of thing. Also, it depends, like if we're counting it from when we originally were given the set of data, and then we ran Floyd's build heap on it, who knows where things are going to end up after that. So Floyd's build heap will definitely destroy it. Or if for some reason somebody actually gave you your data originally in heap form, which would be just gosh darn nice of them, that swapping would probably also disrupt it. Any other questions? Cool. Okay, so exercise 5 is due today. Exercise 6, your last exercise, goes out today. Also, your P4 checkpoint is tonight at midnight. Our wonderful infrastructure TA team is literally just going to go and pull down what everybody's scores are. Is it Sunday? Thank you. Somebody reminded me that it was Sunday, not Friday, and it's been stuck as Friday in my head. Ignore that. You have until Sunday. Does it feel like I just snuck in some free time there? No, just me? Okay, so you have until Sunday. You're right. Surprise. Okay, Sunday. You have until Sunday. So Sunday at midnight, our wonderful TAs will go and they'll just pull down what your current scores are. So if you have 15 out of 30, then you get 3 extra credit points added to your extra credit point total, i.e. the equivalent of filling out 3 pull everywheres. Reminder that P4 is due the Wednesday of week 10, and office hours has still been dangerously quiet, y'all. The TAs and I are actively starting to get real concerned about how week 9 is gonna shake out. I promise you, we didn't give you 3 weeks on this assignment just for funsies. We gave you 3 weeks because we think it takes 3 weeks. And on Sunday, you'll only have a week and a half left. And this is a very uncomfortable assignment to do in a week and a half. So please start now. I promise you, you'll be thankful. Does anybody have any administrative questions? Casey, when are we getting our midterm grades back? It's week 9, or it's week 8. Why haven't we seen the midterm grades? I promise we have been grading a bunch. I did ask the TAs to sort of push and get the grades done by today. Right before lecture, I took a look, and I think there was 10% of the grading left to finish. So I'm hoping that we'll be able to release your midterm grades a little later today. And it will follow the same pattern as the exercises, where we'll release the grades so that you can look at them. And then we'll open up the regrade requests about 24 hours after we release your grades, and the regrade requests will remain open for a week. Yeah?
Just based on how long it's been taking to grade the midterm, are you going to change the style of the final?
Yes, we are going to change the style of the final. Thank you, everyone, and especially the TAs, for being part of this experiment of mine. But right now, we do have the final exam questions written, and it's looking like it's going to be a pretty standard take-home exam, because I don't know, it's the end of the year and maybe we all just need a break. So chances are it'll probably be a standard take-home exam. It'll open up the Wednesday of week 10. You'll have probably a week to complete it. We might shorten that a little bit just because it was written to be a 2-hour exam, so we might give you 4 days to do it, kind of thing. Yeah. Hopefully in a few hours, but we'll make a big ed post when that happens. Yeah, cool. Okay, more sorts. Yay! So I told you there was a few different algorithm design patterns. So we've already talked about the iterative approach. That's where those nested for loops come from. With each iteration, we're putting something where it belongs. And then we were like, what about the data structure approach? Just like dump it into a data structure and then pull it out of the data structure. Here's our third strategy, divide and conquer. And I know I made this really annoying soapboxy claim, but is not all engineering divide and conquer? And so that's really where we're at. And so really what we mean when we say divide and conquer is take your task, which is probably a complicated task, and then break it into a smaller task, and break it into a smaller task, and break it into a smaller task, and smaller task, and smaller task, until you get down to what is arguably the, like, base unit of work you can do, which in the world of sorting is a list of one item. A list of one item is already sorted. So that's our base case, and then we're going to combine that stuff back together as our sort of recursive calls end up sort of completing, and then we'll end up with a sorted collection at the completion of all the calls. Let's meet one. Oh yeah, yes, divide, recombine, great, divide and conquer, okay, yes. Okay, all right, welcome to MergeSort. MergeSort, man, MergeSort is definitely like an A-list celebrity when it comes to sorts. Everybody is obsessed with MergeSort, and for decently good reasons, but it is probably one of the sorts that will get brought up by name most often, especially in interviews. And so the way that MergeSort works is we are going to do that divide and conquer like I mentioned. And so what we're going to do is when we initially get a set of things to sort, like this list up here, we're going to realize like, oh, hey, sorting 8 things is really hard. So I'm going to divide it, and maybe it's easier to sort 2 lists of 4. But maybe that's too hard too, and we're going to divide those again into 2 lists of 2. But maybe that's too hard, and then we're going to keep dividing until we get to our base case, which is a list of a single item. And then we're like, great, that's sorted. An item by itself is sorted. And then what we're actually going to do is we're going to do that sort of logic of deciding who comes before whom when we recombine things. So here, after we've sort of broken everything apart, then we're going to compare 2 sorted lists, and we're going to interweave their members together until we get a recombined sorted list. So for example, you can see here's like a sorted 4 item list. So this is sort of recombined a couple times. And then here's a sorted 4 list. And then eventually we just go through and we interweave things to get to the final sort. Yes?
If the number of element is an odd number, what should we do?
If the number is odd, I think the extra number just sort of hangs out here on the left-hand side. So you always just sort of divide by 2, and integer division just sort of takes care of the oddness for you. So if this had 9 elements in it, then we would have divided it probably into a set of 4 and a set of 5. And then that set of 5, we would have divided it into a set of 2 and a set of 3. And then that 3, we would have divided into a set of 1 and a set of 2. And we would have just had to iterate one more time to get that set of 2 to break apart. Good questions, though. Yeah. How do we sort the... Oh, so how, okay, so, and what we're going to do is when we are recombining, we're always going to go by taking 2 lists and recombining them into a singular list. And we're going to do that at a few different levels. So, you know, previously, like from this step, we combined the 2 and the 8. And when we did that, we looked at each of these items and we said, who comes first, the 2 or the 8? And then hopefully we decided the 2 came before the 8. And then I had a list that said 2, 8, and I had to recombine that with a list that was 22 and 91. And then I sort of interwove those things by having pointers at the start of each of the arrays I'm recombining. And I'm asking myself, who's smaller? Move into the new array, move my pointer. Who's smaller? Move into the new array, possibly move my pointer. And so in this last step here, I've got an already sorted list of 2 4s. So I'm going to start looking at index 0 of each of the 4s, and I'm going to ask whose index 0 is smaller. It's the right-hand one, so the 1 takes that spot, and then that little pointer probably moves over, and then I will ask who's smaller, the 2 or the 6. Well, the 2 does, so the 2 ends up there, and then I move my pointer over. Now my pointer's at the 8 and the 6, and I ask who's smaller? It's the 6, so I put that there. And then I move my pointer, and I ask who's smaller, the 7 or the 8? Oh, the 7, so I pull another one from this, and so I do this sort of interweaving. Maybe we should watch a visualization. The joy of the algorithmics. You could watch so many different types of sorts out on the internet, but aren't you like, oh, thank goodness Casey picked the most annoying one to subject us all to in lecture. Huzzah. Oh, look how serious they are. Yes. Okay, so here we have our big array. First thing we're going to do, divide right down the middle. We're like, we don't know how to sort 10 things. Oh, but we don't know how to sort 5 things, so we're going to split that into a 2 and a 3. And then, there we go. We're going to split apart there again, too. Now I'm going to speed this up. Otherwise, we'll be here for forever. And so you can see what just happened there is they split up and they just recombined. Now they split up. There's my base case, 8's by yourself. I split up the 6 and the 0. Now they are recombining. 0 comes before 6. They come back together. Now they are going to compare. Where does the 8 go? Now the 3 are finally reunited as a sorted collection. Now it's time for the 2-4 group to find their way together with the 0-6-8 group. And so you can see there, they're sort of comparing each other at the front, and then 8 just kind of slides in there at the very end. Huzzah, they've done it. Good job. And then, yes, we do the exact same thing. We split. Then they decide who comes first. 1 comes before 5. They recombine. We split apart. 7 is his own base case. We split apart. Now they're base cases. They recombine. 3 comes before 9. Now we've got to recombine with the 7. Yes. And now we've got our reunified group of 3. Now we're comparing with that other group of 2. And we're doing this interweaving, as you can see there. And now we've got 2 sorted lists of 5. We're going to do this interweaving. And you can see it's always the people at the sort of front of the queue that are comparing themselves to one another, or the front of the array. Huzzah, they find their partners, yay! And then finally we fill it out. Oh, they didn't have a little celebration at the end. Any questions on how MergeSort algorithm works? There we go. Okay, so the divide is just break it down, break it down, break it down until we hit the base case. And then through the magic of recursion, we sort things together. And here, this is a much nicer slide with the pointers. This is exactly the thing I was sort of describing, and my pointers aren't moving, but you can see how that happens. Here is another visualization, so on and so forth. And you can see MergeSort is inherently a recursive function. We call MergeSort on the 2 halves, and then we merge things together after we have split things apart. Okay. So, we are going to do this thing where we have originally our sort of collection, right? And we're going to split the amount of input into each recursive call in half, right? Like if we look at each of these recursive calls, they both take in n over 2 because we're distributing the n across 2 recursive calls. So each subsequent recursive call gets half of the n of its previous recursive call. Any intuitions on what type of runtime we get when we take the input and we divide it in half and divide it in half and divide it in half over and over again? Hint, binary search. Yeah, so here's a delightful recurrence for you. Like I said, when I taught this class, pretty much every other quarter, I made you do like a bunch of algebra, but that is just n log n. you don't have to worry about the outro anymore. Yes. So the worst case runtime of MergeSort is n log n. The log n comes from that divide, and the n comes from at each level, we still have to go through and interweave things back together. And that interweaving, because remember I sort of had my like pointers at the beginning of each of the arrays I'm recombining, and then eventually my pointers sort of make their way from the beginning of each array to the end of each array. That incurs that linear runtime. So that n factor comes from the like recombining aspect. The log n comes from the sort of division aspect, which is a little easier to see, you know, when we put it in this recurrence with this n over 2 hanging out over here. This plus n is the interweaving. The n over 2 is that dividing. So then maybe a more interesting question is this the runtime regardless of the state of the data? Is there a difference between the best case and the worst case for MergeSort? If it was already sorted, is MergeSort going to stop and not have to divide or not have to bring things together? No. Okay, great. Yeah, same. Yes, exactly. So the thing about MergeSort is MergeSort literally runs exactly the same algorithm no matter what every single time. Totally sorted list, it's still got to break it all apart, and then it just like will do the same interweaving thing, but nothing will be interwoven. It'll just sort of like dump everything from the first array in and then dump everything from the second array, but you still have to touch everything. So MergeSort is an n log n, n log n, n log n kind of situation, which is nice because it is very predictable. So you will find that actually Java's arrays.sort, if you are using objects, if you're trying to sort objects, meaning you've got to call .compare_to a bunch, then Java actually uses MergeSort as its under the hood sort. Is this algorithm stable? Do we mess up the original order of these items at any point? MergeSort is stable because though we break everything apart, we always approach it from the original left-right order. Like even when we're interweaving, right, I'm interweaving things from the left to the right. There's no any like sort of spontaneous swapping something out to the back of the array or running void's build heap that totally destroys it. It's very programmatic. So it is a stable sort, which is also really nice. Is this an in-place sort? No. Look at how many arrays are on the screen right now. And remember, arrays like can't grow or shrink. So that means I had to duplicate the memory at every single recursive level. So it is definitely not an in-place sort. So like I said, MergeSort is one of the most popular sorts. We talk about it a ton because it's just really predictable. It runs in n log n time every time. There's no dangerous worst case, but we got to be willing to eat that extra memory usage because MergeSort is really expensive from a memory perspective, which shouldn't be that surprising because hopefully at this point we feel very comfortable recognizing that, gosh darn it, recursive code, really memory exhaustive. Any questions about this? Yeah.
We just make some pointers to show that we treat the array like it's
So can we do a thing where we have a bunch of pointers so we don't actually have to split things out into their own array and turn this into an in-place sort? There is a version of MergeSort that is implemented in place, and it does still have like this n log n theoretical runtime, but it turns out implementing all of those pointers and updating all those pointers and all those variables actually end up becoming so unwieldy. It is a real bear to implement, and what we call the constant factors of all of those like pointers and things like that actually end up slowing this down pretty significantly. So you'll find that actually much more often this is implemented with the recursive not in place form. But what a great seed of an idea for another sort. All right, let's meet our last sort. Our final sort, and I do kind of save the best for last, is called QuickSort. And it's going to follow the same general idea where we're going to divide and conquer, where we're sort of splitting things into arrays. But MergeSort was like, don't worry about the sorting, just split down to the base case, and then sort on the way back up. QuickSort's kind of the inverse of that. This time, we're going to do a lot of the logic in the beginning to sort of like pivot around a particular number, and then when we recombine, we just kind of got to mush things back together. Let's take a look at it. So, the way that QuickSort works is with QuickSort, you are always going to pick what's called a pivot. And the pivot is going to be the value that you compare all the other values to. So, in this case, I just picked the item that was at index 0, which is actually a very common approach to implementing QuickSort. It's just like, just grab whatever's at the beginning of the list. And then what I have done here is I have split my list technically into two separate lists with a pivot in the middle. And everything to the left is something that is smaller than the pivot, and everything to the right is something that's greater than the pivot. I haven't fully sorted it. You can see this array here. This is not sorted order, but all of these items are less than 8. Because all I did was I picked my pivot as 8, and then I looked at this value and I said, is 2 less than 8? Put it in the left one. 91, is that less than 8? No, put it in the right one. 22, is it less than 8? No, put it in the right one. 55, no, put it in the right one. 1, yes. 7, 6, and then I've got my pivot hanging out here. And then I'm going to repeat the same thing where I'm going to pick two pivots now. A pivot for this group and a pivot for this group. I don't need to pick a pivot for the 8. The 8 is already at a base case. 8's hanging out by itself. But I'm going to pick another pivot for 2. I'm going to split this 4 into its own little like group of 2, a pivot, and then a group of 1. And then I'll do the same thing here where I'll pick the pivot of 91, and then I'll split the 25 and the 55 around it. And eventually you just split and split and split until you get down to everybody's in their own category. And by the time everybody's in their own category, they are sorted because we've pivoted enough times. And so then we just got to put everything back together. Shall we watch? Okay. Okay, so there's my pivot. And we have decided 6. I can't even see. Wait, what is our pivot? Our pivot's 3. Okay, so see how they get the hats. 6 is greater than the pivot. 9 is greater than the pivot. 4 is greater than the pivot. 5 is greater than the pivot. So they're all just kind of staying in the relative order, but they're staying to the right. Now 2, 2, yes, indeed, you are smaller than the pivot. And so 2 finds their way to the front of the array. And then we compare 0. Oh, 0, you are also up. 1, there we go. Also in the same thing. 8, where do you go? Up. Now you're going to kind of, okay, yes, you're going to swap over there. And so you can see actually what they're doing in this case is notice they're kind of like just trading places because this is an in-place implementation where they're just sort of using that space within the original array. And now 3, his job as a pivot is well accomplished. And so then we picked a new pivot for the small group. It was the 2, I guess. Ta-da, yes. Oh, and then 2's job as pivot is done. There was no right-hand group. There was only left-hand group. And so they do their dance. And they break apart. And then they both become the pivot of themselves. And they're done. Yep. There's a lot of hats in this one. There we go. And then we do the same thing over here. And we're asking ourselves, do we pivot? But look at how the gentlemen on the left-hand side that have all been pivots, they're already in sorted order, right? Like they're already standing in the order they should be standing, which is nice. There we go. 4 and 7. Finally, yes, pivot off to the other side. And so they just literally swapped places is what happened there. And then we looked at the other item, 5. Where do you belong? You're fine. You stay there. There we go. Aha! Then we do it again. And so you can see 6 picks as the pivot, compare 6 and 5. 5 goes to the left. Okay, I'm pretty sure they even sped up this video now, so we're doing double time on whatever speed they've got it going on, or maybe they're just incredibly talented. Huzzah, huzzah, okay. And then eventually we get down... I can't tell the difference between the hats, but I feel like maybe there's something important about, like maybe the hat with... Oh, I think maybe the hats with feathers indicate that they're currently acting as pivot. Yep. There he's the pivot of himself. You're in the right spot now, sir. Yes, and then 9 and 8, they do their dance. There we go. Base case. Okay. Aha! And then they were all in sorted order. Amazing! And they just have to recombine. Wow, they get a great celebration dance. Oh, yes! My goodness. Okay, actually, this is amazing. All right, you're fair. That is the last algorithmics video I will play for you. But look at, they even do the end queens, y'all. So if you really want to get deep into the YouTube wormhole, there's plenty of enjoyable stuff there. Okay, so this is fine. We talked about this. There's the site pivots. There we go. Combine, interweave. Sounds good. Okay. There we go. Great. Okay. So, what do we think then is the... Maybe I'll start with the best case runtime. Now remember how we learned about best cases with trees? The best case of a tree is when the tree is full or balanced, right? Because when a tree is totally full or balanced, every decision cuts the inputs perfectly in half. And that's like the most amount of things we can eliminate, right? And so you can imagine, like, we're just literally randomly grabbing the first thing in the list. Wouldn't it be gosh darn convenient if that thing in the list that's at the very front was the perfect median value? Because then the two lists that would get pivoted on either side are perfectly halved, meaning one's not exponentially bigger than the other, which means they're both going to get down to the base case at about the same level. So, the best case scenario in this situation is when at each pivot we end up with two lists that are in equal size, meaning we've split the input perfectly in half across the less thans and the greater thans. What do we think the runtime is of an algorithm that splits our input at half perfectly at every level? Yes, good job everyone, n log n. So the log n is from that perfect splitting, the n comes from us recombining at the end. But, unlike MergeSort, QuickSort isn't always perfectly dividing in half. We're letting the pivot be the decider. So, can anyone guess, for example, what would be the least optimal pivot? What would be the most inconvenient pivot? Yeah. Exactly. The smallest or largest value. Because what would happen is then we would pull the pivot out, and let's say it's the smallest value, and every other value on the list, we'd be like, are you smaller than me? No. Go back to the right-hand side. And then we would just end up with a pivot and then n-1 items. And we would have to call a recursive call on n-1 items. And then let's imagine on that n-1 set, we picked the front pivot again. And what if it was again the second smallest item in the list? And then we pivoted and nobody ended on the left-hand side. So again, we call a recursive call on that time n-2, and then n-3, and then n-4. So we're not dividing in half, we're just only shaving off the pivot at each level. Does anybody want to guess what that runtime is? I'll be surprised. Yes, n squared. Because there you go, there's that n-1. So QuickSort does have an n squared worst case runtime, and it actually happens when the list is already sorted. Darn you, QuickSort. but its best case is n log n. And I know it's 3:20 and it's a Friday. Come back on Monday and I will convince you why the actual runtime of QuickSort earns its name as truly the quickest of the sorts. Thanks so much, everybody. Have a great weekend. Checkpoint on Sunday, not Friday. Checkpoint on Sunday.